All right, so let's move on. We will now extend our perceptron classifier bit by bit to eventually arrive at a proper neural network. First of all, we extend the model. We by now know pretty well. You'll see it on the left-hand side of the slide one more time. We extend it in such a way that we add two more things. Make sure you spend a little time to check the picture. What are the two additions? Well, we have a second output. Previously, we were producing one output, one classification or classifier score, y hat 1. Now we also had y hat 2. So in neural networking terminology, we have introduced a second output node or neuron. And in addition, it's independent from the second output node, it's just a second extension that we've been doing here of the perceptron. Here, we also have a second node, internal node, it's internal, and these are called hidden nodes or hidden units or hidden neurons. So what does that mean? For now we will consider networks where every unit is fully connected with every unit of the next layer. That means that if I draw three input units, x1, x2 and then xm, so in practice there would be more, as many input units as there are features. Then in a fully connected network, every one of these input units has a link to the unit of the next layer, our hidden layer. Slightly alert that my graph might be too cluttered in the end. We can call that the hidden layer because it's the part or layer of our small network where the hidden units live. And then on the other side from here there would be the input layer. Input layer, and then, well, guess what? This part is called the output layer. So our output layer has 2 units, our hidden layer has 2 units, and our input layer has 3 units. And our network is fully connected. And probably this is the most important thing on this picture here. You have all these additional parameters, all these additional weights, all these additional W, where by now we also need to use a second index in order to tell them apart and to depict which connections they weight and where these connections are going. Let's look at the equations that correspond to this extended perceptron with 2 hidden and 2 output units. So same perceptron as before. And you see how, or now you can guess that at some point writing the equations or writing out sums becomes very inconvenient, whereas matrix notation is much more concise. You already see that here. First of all, we have input data. We have observations. Previously, I was using the example of borrowers that apply for a loan with a financial institution. So one column in my matrix X would represent one borrower. So this here could be John, that could be Mary. I'm referring to the table that I was using earlier on in the presentation, right? One column vector in this matrix X corresponds to one of our data points. our customers, clients, whatever, data points, right? And then we have a weight matrix, capital W, where we have all the weights, or in this simple neural network or simple extended perceptron is already a neural network. We need only one weight matrix to store all the relevant weights, namely those weights that connect the input units to the hidden units, to our two hidden units. Because we have two, our weight matrix has two columns, and since we have three input units, we see three rows in our weight matrix. And that certainly is always the case. The weights between the input and the hidden layer, we can store them in matrix format, and the dimensionality of this matrix will always be the dimensionality of the input layer, the number of units in the input layer, times the number of units in the hidden layer. While the number of input units, M, is of course equivalent to the number of features in a dataset. We also have our bias vector, or our hidden layer bias vector, and then we can write out the equation that leads to our scores, denoted by Z. In this way, Z is equal to WO plus X transpose W. And you can convince yourself that if the matrices X and W are oriented in this way, then we need the transpose of X in order to compute what we are really interested in computing, all the values of the input features, X1, 2, all the way up to M, times the corresponding weights. And for example, for John, if we take the transpose of John and then we multiply X with W, we get basically two output values, which are Z1 and Z2, that come from X transpose times W. It's maybe sensible that you spend a little bit of time to really make sure that you fully grasp these computations and that they make sense. So I realized that it would be a good idea to also write down Z. I'm a bit unhappy here because I just realized that strictly that should not be capitalized, because it should be bold though. So bold. It's the vector of Z1, Z2, which comes out of the multiplication. And you also see in the graph on the left-hand side where we have these values and where we then put them again through some activation function. By now, you should not be too surprised by that term. You see the yellow nodes in my graph. These were the nonlinear functions, these activation functions. And subsequently, we get the two outputs, y hat 1 and y hat 2, which could be, for example, in a multi-class problem where we deal with two different or with more than two different classes, the corresponding probabilities for one class and the other. So that is a perceptron with two outputs and two units in the hidden layer. And well, obviously what we just did, we could extend it further. No need to only have two units in the hidden layer. You can ask yourself, okay, what would happen if I add another one of these hidden layer neuron? How does that change the picture? Well, no need to draw it. I did it for you. Here is how the picture changes. I added two more hidden units. And what we see here in this graph is a proper neural network, feed-forward neural network, or it is also called an MLP, a multi-layer perceptron. It's a perceptron with multiple layers. Or, well, strictly speaking, it's multiple perceptrons. But, well, let's not go there. I did not write weights on all the connections because I felt that the graph would get too cluttered. But you do see these two matrices, W superscript 1 and W superscript 2. So it's yet another extension of the picture. And I want to walk you through these computations one more in quite some detail in order to ensure that you really internalize the mathematical operations that happen here. And what we see at the right hand side at the moment is the computation for a single unit in the hidden layer. So the computation for one element of the hidden layer, zk, where we do have some bias connected to that layer, and let me pick this one. So this value here, if we set k equal to 1 for a minute, then that would be the corresponding weight and where we find it in our graph. So the value of Z1 is determined by whatever weight is found for this connection from the bias connected to this hidden unit into it. And in addition, we have the summation of all our inputs, x1, x2, all the way up to xm, times their corresponding connection weight, wjk. So this is the weight from the connection of input j into hidden unit k. That's why we need the double indexing here. And if you wonder about the superscript, the 1, that's also important because especially in deep neural networks where we have more than just one hidden layer, we need to tell apart the weights in one hidden layer from those in another hidden layer. So I admit that for this still fairly simple neural network, the notation might appear a little bit of an overkill, but I'm trying to ready you for the general case where we have deep nets with many of these hidden layers. But okay, let's stick to this simple net for the time being. So we have seen how one input unit is calculated. That's beautiful. And we could also write that down in matrix form, in matrix notation. And then using capital Z here is to represent that we are calculating all the weights of the input to hidden calculation in one go. So we take our input x, we multiply it in one go with the weight matrix W1, which has dimensionality 3 by, let's say this is 3, then we have dimensionality 3 by 4 in our weight matrix. And if we then compute x transpose times W1, we get this 1 by 4 output vector Z. So in this example, Z is 4 by 1. All right. Okay, I hope you are okay with the computation so far, so that we can move on one step ahead. We basically calculated the forward path of input data through our neural network up to, well, this point. We've calculated the input signal to our hidden layer, aggregating all the values that come in, and we computed the hidden layer vector z. And the next step will be, indeed, now we want to add some nonlinearity. Now we would apply these activation functions. So in the next step, we take what we just had and put that through our function g. So g is a function that we apply to our hidden layer vector z. And the g of that does then give us a vector of the same dimension as that. I denote it by h. We can call that the hidden layer output vector. That's a useful way to think about it. We spent a little bit of time on the perceptron to ensure that we understand in these computational units, in one of these neuron or units or nodes, there are two operations: aggregation of the input and then the nonlinearity, the S-shape. Okay, so that's exactly what's happening here. We have somehow I want this in black color. We have the vector z, and yeah, it's all bold, it's vectors, which is which we could call our hidden layer input, and this h then is our hidden layer output. It's very important that we keep these two bits distinguished from one another. It's sometimes also called the activation of the hidden layer for this specific data point. It's also useful to point out. Look at this bit here. It's small x. We are putting one data point, one observation, one credit application or whatever to through our neural network. One data point meaning one feature value for x1, bureau score maybe, one feature value for the second feature, salary, one feature value for the third feature, age maybe. These are all the input feature values. And if you think about it, it's important that I put value here, right? So the data that comes in are the values for the features of one data point, one customer, one borrower. This data comes in here. And then we put it through our neural network. First of all, we weight it using the weight matrix W superscript 1. We add an intercept. This gives us the hidden layer input. And with this hidden layer input, we then move on, apply some nonlinear function, apply some activation function. That gives us the hidden layer output. And the hidden layer output then goes to the output layer, where in this example we have two neurons. That means that, and here you see it in detail, from every unit of the hidden layer, we have a connection into these output neurons. And on these connections, we also have weights. So now we are taking the hidden layer output, which are 4, in my example, it's 4, because the number of units in the hidden layer is 4. We have these 4 latent features if you have a background in statistics or in econometrics, the term latent feature will ring a bell. If not, don't worry. It's not super important, but for those of you who are familiar with latent variable models, for example, I just want to make sure that you understand that's exactly what's happening here. We calculate these 4 latent features with hidden layer output, and from that we perform pretty much the very same computations as before. We take these outputs, let's move on, and we weight them, and we add an intercept to obtain our final model output. Note these guys here, W, K, C. So it's a weight, it's a scala, which sits on the connection from the hidden node K and connecting that node with the output node C. And because I could have as many as I want to, hidden and output nodes, we need these indices. And again, all these weights that sit on the connections between the hidden layer and the output layer taken together, we can put these into a matrix W superscript 2. And then we can equivalently write out the equation to compute the final output for a given data point x of our neural network, y hat, as WO, the intercept or the bias, plus the hidden layer output times our weight matrix W. I have added some more slides in order to detail these matrices a little bit so that you can really dive deep into the computations and follow along. So this would be the shape of our weight matrix W superscript 1, where we have m by 4 in this example, or more generally, if we agree that the number of hidden units in the hidden layer is d, we could say our first weight matrix has dimensionality m by d, and then our second weight matrix would have dimensionality 4 or d by, previously I used c, whatever is the dimensionality of the output layer, 2 in my example. And then all the computations work out, and here I have one example for y hat 1, the value of our first output node, how we calculate that as a linear function of WO1 superscript 2. That's basically this guy. Then we have W11, so a weight of the, well, superscript 2 of the second layer, if you wish, that connects the first hidden node to the first output node, 1, 1. And it's multiplied by the hidden layer output, G of Z1. So that would essentially be this connection right here. And then we have the output of the second hidden layer node, G of Z2, which we multiply with the weight W21. And maybe I should stop before you will not be able to see anything in the graph, or before I make errors. There would be this connection here, where of course we have one weight sitting and being multiplied with the corresponding output. And so forth. We also have that for the 2 more nodes of the hidden layer. And the same obviously is true for y hat 2. Same rules apply. Maybe it's a little exercise. Write down by hand the corresponding equation. And well, you see here this chain of recurrent operations where we have inputs. We multiply them with weights. That's essentially just linear algebra. And the result of that, we add some nonlinearity to it. And then we repeat this operation. We take our latent features, our Z, or well, more specifically, our output of the hidden layer, our H, multiply that with weights, add nonlinearity, and move on and move on and move on. That is the idea. It's a chain of algebra times nonlinearity, algebra, nonlinearity, more algebra, more nonlinearity, and so forth. And we can continue these chain of operations as long as we like. So we can, first of all, add as many computational units as we like. We have the perceptron again, and I was trying to highlight here how one of these units in these graphs always represents two operations: input aggregation, you have the sum, and nonlinearity, you have this, well, that's my attempt to draw an S-shaped function, right? And we can have many of these units in the hidden layer, making our network bigger and bigger and bigger and bigger. But not only that, as I was already indicating, we can also chain together these layers. So from a single hidden layer network, by adding more of these layers, we can construct a multi-layer neural network. And if we have many of these layers, don't ask me how many, I can't tell you, but if we have many, then we can call our network a deep network because there are so many layers. So that would be a deep, well, it's written in the header, right? It's a deep NN, deep neural network. And you can guess that if we want to write out the equations rigorously, we need to be careful and we need many indices and superscripts and etc. But it's absolutely not any different from what we just did. And this is exactly why we were taking slow steps: perceptron, one hidden layer neural network, deep network. And I was trying to spill out the equation for one hidden layer node, for node k, zkl, that would be the k hidden node of the lth hidden layer. So the first index here, the L, that is layers, while the K is nodes per, say, layer, right? Okay. And yeah, for a single node, no matter in which layer this node is located, it will have an input. So we have W superscript L. It's an input, it's a bias node of the Lth layer. OK. K is the hidden unit once more. And in addition, we will have all the signals that come from the previous layer. The previous layer in a deep neural network will normally be a preceding hidden layer. So the output of this preceding hidden layer is that time the input on with nonlinearity. So this bit here is the output of the previous hidden layer. More specifically, since I'm writing out the sum, it is 1. That's inaccurate. Let me take that back. It's the output of, I need to take it back even more. So it's the output of 1 node L minus. You see how this is complicated. Of 1 node J of the, should be proper English, previous hidden layer L minus 1. And this hidden unit is connected to our hidden unit ZLK, and on this connection we will find a weight which is just WJK from hidden node J of layer L-1 into hidden node K of layer L. It is a little bit complicated, but if you really think about it, the main complication is maybe to write out the indices properly. Conceptually, it's just what we have seen before. And actually this makes sense if you think about it. I was saying before that what's happening in these neural networks is that the hidden layer computes something like a latent feature. We start our modeling problem, our classification problem. We start that with some input data, and ultimately we want to obtain some predictions. And the neural network, it approaches this problem by taking the input data and putting that to the first hidden layer, which has some size, 3, 4, 5, 6, whatever hidden units. And each of these units aggregates the information from the input, weights it differently and from reality. So we are computing these latent features. Okay? And then we move on. These latent features that we compute in the first hidden layer, they actually represent the input for the next layer. It's really a chain of neural networks, just that our input data have been transformed into our input features have been transformed into some latent features after the first hidden layer. And if we continue, with each layer, our input features get transformed more and more. But it's always this operation, taking all the input from the previous layer, aggregating them, weighting them, adding them up, putting them through some nonlinear function, and putting out or forwarding the corresponding result. That really is the idea. Right, and yeah, that should give you a pretty good understanding of what a neural network is. And before you get the impression, which sometimes might occur, deep networks, that is super simple, it's just one of these networks with hidden units, and then many of these layers. It's actually a little bit more than that. So the space of deep learning, you see here represented in a wonderful graph, I feel, by colleagues from the Asimov Institute, where they try to come up with a notation. You might even go so far to call that a type of modeling language, where they highlight the many different types of layers and computational units that exist in the scope of deep learning. Obviously we are not yet ready to make sense out of all of these graphs and all of these different types of neural networks. The point I'm trying to make is essentially, on the one hand, this idea of having a network with many computational layers and then calling that a deep network is true, that is accurate. it is, if you have many layers, it is a deep neural network, and by now you are basically there. You understand how the computation happen. What we haven't talked about is how the weights are trained, how we come up with good weights, but we'll do so in the next lecture. So that bit you already have obtained, you already learned that, which is great. It's just that if we talk about deep learning, then please bear in mind, too early to stop the course. There is much more to discover, and deep learning is much more because we have many different types of neural networks that also have the same idea of layers with units, but the computations work in a different way to make these networks more suitable for certain tasks, like processing images or text, for example. All right.